about conservative and non-conservative forces last time. So we saw the very interesting property of conservative forces that, good evening everyone. So we saw the very interesting property of conservative forces that the work done is independent of path and depends only on the final position and initial position. Whereas non-conservative forces, the work done is path dependent. And we also saw kinetic friction as an example of non-conservative force. So let's continue ahead with that today. So work, power and energy. This will be session number 3 for us. So before we jump into more examples, we will see another important property of conservative forces. Conservative forces is such that work done is path independent. This we've already seen, that is the definition. That means this basically implies that the work done depends only on the final and initial position. Okay, so therefore this also implies another very important thing, that if the path is a closed loop, okay, or what in physics is also called a round trip. So round trip doesn't exactly mean that the shape of the path has to be a perfect round circle, but it means that it's a closed loop, which means that the final position is at the initial position. The final position is back to the initial position. So if the path is a closed loop, the work done by a conservative force must be zero. So this is a very important property which you must note down of a conservative force, that in a closed loop path or in a round trip path, the work done by a conservative force must be zero. It cannot be non-zero. So these two statements are actually implications of each other. If the work done is path independent, it means that the work done in a round trip or closed loop must be zero. So just start by noting this point down. We'll discuss further about this. So for non-conservative force versus, it becomes opposite. The work done will be non-zero in a round trip. So it's like the inverse of this statement. For non-conservative forces, the work done is path dependent. That means even in a round trip, the work done will be non-zero. Okay, so the fact that it is path dependent now implies that work done in a closed loop path or round trip will be non-zero. Okay, for non-conservative forces, of course. Yeah, we'll discuss both this examples. So the easiest example, Karan, you can think of for conservative force is constant force. So for example, any constant force is conservative because work done by constant force is F dot S. If F is conservative, sorry, is constant. Okay. Now for a round trip, for a closed loop path, for example, a body starts from here and comes back to where it started. Okay. So B is equal to A to B, but back to that same position A. This is an example. Okay. So what will happen for a closed loop? The displacement will be zero. Okay. So therefore, work done has to be zero. Okay. So it satisfies that condition. But the thing is, this is just one example. Conservative force is not just only constant forces. There are variable forces also which can be conservative. And we will show one such example also, for which again, we'll be able to show that the work done in a round trip will be zero. Okay, write this down fast, please, people. Okay, done. Let's look at another example of conservative force. Now this time we'll take a variable force like spring force. Yeah. Spring force. We know it is conservative. Now let's demonstrate the work done by a spring in a round trip is zero. So suppose we have a spring at natural length position initially. Okay. And from here, some external agent starts pulling the force. I mean, pulling the spring, takes it from this position A initially to this position B, let's say, where the spring has stretched to L plus X1. Okay. Then allows it to come back and actually pushes it so that the spring comes to now this position C, where it's actually got compressed to this A. And then again, eventually allows the spring to come back to its natural length state. So back to A, where it started from. Okay. So A to B to C to A. This is a round trip. This is a, I mean, it's not round in shape, but it's a round trip because, okay, the final position is back to the initial state. Okay. So the work done by the spring force in the round trip, this particular round trip, will be the work done by the spring force from A to B plus the work done from B to C plus the work done from C to A. Now we'll be able to show very easily that this will be zero. Okay, because you can individually show that going from A to B, what is happening is that at any point of time in between, if your spring is stretched by x, the spring force is acting in this direction and your differential displacement is in this direction. So the work done by the spring from A to B is minus kx dx, integrated from A where x was 0 to B where x is equal to x1. So it is minus half kx1 square. Okay. Then when you're going from B to C, what is happening? Again, the direction of the spring force and displacement are opposite, but this time you're going from B where x is equal to x1 to C where x is equal to minus x2. So it is again minus half kx square by 2, but the limit going from x1 to x equal to minus x2. Okay, so it is minus half k x2 square minus x1 square. This is the work done from B to C. Okay, this was the work done from A to B. And likewise, when you're coming back from C to A, okay, at some point of time, your spring is compressed by X. So it's pushing the block in this way, and the displacement is happening in this manner. So again, the work done by the spring from C to A will be minus x2 to x equal to 0. Okay, so this is C to A. So now I've got the three individual terms. Now put them in this equation here. Put them in this equation here, all the three terms, and you'll get that the net work done in the round trip will become minus half kx1 square minus half k x2 square minus x1 square plus half kx2 square. You'll see the terms cancel and you'll get it as 0. Okay. So this is just a way to demonstrate that the spring force is conservative. Therefore, the work done in a round trip will be 0. So in simple terms, what we are saying is that if the spring goes from 0 to extension, it does negative work. Now, in coming back from extension to 0, it does equal and opposite positive work. And same for compression. When you compress the spring is doing negative work. But when the spring is coming back from compression to natural length, it's doing positive work. So if you're coming back to whatever state you started from, always the net work done by the spring will be 0 because the negative and positive part of the work done will cancel each other. So that is what the exact calculation here is also showing. Kx beta, spring force Kx hota hai na. Dx to displacement. See, dx is a small displacement. Spring force kaisa hota hai? Spring force is minus kx, no? So if x is positive, then the direction of the spring force is negative. If x is negative, then the direction of the spring force is positive. So that is why work done by spring force minus kx dx integration, this always gives you it's negative if mod x is increasing and it's positive if mod x is decreasing. Okay. So whether you're compressing or expanding the spring, if you're deforming it more than what it was deformed earlier, the spring force will be doing negative work. And if you're bringing it from deformity back towards natural length, then your mod x is decreasing, so it will be doing positive work. So this nature of this symmetry of the work done, that when you go from 0 to compression, it does negative work, but compression back to 0 is doing equal and opposite positive work, and vice versa for extension. That symmetry actually demonstrates why the force is conservative. and the work done in a round trip will be 0. Okay, so this is an important example. It demonstrates that work done in a round trip is 0, which has to be the case because we already know that spring force is conservative in nature. Okay, so let's go through this once more in detail. So this is what I'm doing actually, I'm going from natural length to extension first. So I'm extending from x equal to 0 to x equal to x1, and that is giving me this work. Then next what I'm doing, I'm taking it from there to compression, to a compression of x equal to minus x2. So that is the second part which is giving me this work done, B to C, which you will see below this part. Okay, and then I'm bringing it back to natural length. So that's the round trip. So the net work done in this round trip, it will come out to be 0 because spring force is conservative. Now for each individual subpart, I will calculate A to B, then B to C, then from C back to A. We'll calculate the work done by this integration method. Is it clear now, Diti? Okay, so we'll come to the second part, the work done from B to C. That's this part. Okay, so this was the first part, the work done from A to B. Then this was the second part, the work done from B to C. And finally, this is the third part, the work done from C to A. Okay, so now finally the work done in the round trip. This part is the work done in the round trip. So we can write it like this. It's AB plus BC plus CA. So this is becoming this, which you can see is going to be 0. Whatever the values of x1 and x2, whether it's plus 5 centimeters, minus 3 centimeters, whatever the individual numerical values, but the total will have to be 0. Okay, so hope this example is fully clear. Now let's come to an example of non-conservative force and show how the work done in a round trip will become non-zero. So very simple example of that is, suppose we have a rough surface and what we do is a block of mass m. Okay, so this has got a coefficient of friction mu, and we are pushing this block with an external force so that initially it goes from A to B, where this distance is S, suppose. So work done by friction from A to B will become how much? Minus mu mg S, because you can see that at any point of time, the forces acting are mg normal reaction, the external force, whatever we are applying to keep it moving, and kinetic friction like this. So that kinetic friction will have a magnitude of mu n, which is mu mg. Okay, and the displacement is in this direction. Okay, so work done by friction is this. So that becomes minus mu mg integration of ds from a to b. So that gives you the work done by friction from a to b as minus mu mgs. Okay. Now if I bring the block again back from b to a, then I'm completing a round trip. Okay. So now I'm bringing the block back from b to a. So I'm giving it a displacement like this now. Okay, by applying external force like this. But this time as I'm going from B to A, friction will again be in the opposite direction. So work done by friction from B to A will become minus mu mgs again. So the total work done in the round trip is how much? It's the sum of two negative quantities, so it can never be zero. So work done by friction from A to B to A, back to A, and this round trip, this is becoming how much? It's just becoming minus 2 mu mgs. Or whatever the values, but it's the sum of two negative quantities, so it's non-zero. Because kinetic friction is a non-conservative force. Okay. So work done in a round trip is not equal to zero. Okay. Now it's not just this round trip. You can visualize any sort of round trip. Like on a horizontal surface, you can take a body on any kind of closed loop like this. Okay. But the work done by friction will be a negative quantity in the closed loop. It won't be zero because friction is all the time going to do negative work as it moves. Okay. Now let's come to a two-dimensional example like we were discussing that day. Okay. So similar type of problem we'll take now. Okay. So in this example, a particle moving in the xy plane experiences a variable force. Oh, you haven't written that down, just a minute. Okay. Yeah, so let's come back to this. So this is going to be a two-dimensional example. So it experiences a variable force given by the relation F is equal to 10 plus 2x I cap plus xy, or let's say 2xy j cap, okay, at position xy. So when a particle is at a point or at a position x comma y, it experiences a variable force given by this formula, where x and y are in meters, okay, and F is in newtons. Okay. Now let us take a situation like we had done last time, that let's take the particle from the origin to any particular point via two different paths, and let's again investigate whether the work done by each path is same or not. Okay. But only this time we'll do a bit of a variation of how we had done the problem last time. So we will take it from the origin to this point P, which is having coordinates, let's say 5,5 in meters, okay, where our first path will be like the path we had taken last time. First along the x-axis and then along the y-axis. So this is our path 1. Our second path this time, we'll do a slightly more complicated situation. We'll take it directly along a straight line from O to P. So this is by path 2. Okay. So calculate the work done by this force for displacement from O to P via path 1. Okay. And secondly, O to P via path 2, which is a direct straight line joining O and P, is given in the question. Everything given is in the question. I have not given any answer or assumption yet. Okay. So the point P, as per part of the question, has coordinates x equal to 5 meters, y equal to 5 meters. Okay, so try this out. At least the first part you can solve yourself quite easily by using the same method that we had in the last lecture. Okay, very good. So a couple of you have sent the answers. Let me just tell you the answer of part A. So for part A, again, it's like that only. If you will calculate the work done first to go along the x-axis. So remember the force is given by this formula 10 plus 2x, was it? Or 5x? 10 plus 2x plus 2xy j cap. Okay. So now, so the first part, I'm going from this point to, let's say, this point A, which is at 5, 0. So when I'm at a general point like this, I'm on the x-axis and my displacement is going to be like this. So O to A, the work done, this integration, F is going to be how much? It is going to be just 10 I cap, and ds is going to be dx I cap. So the work done is going to be 10 dx from x equal to 0 to x equal to 5. So it is going to be 50 joules. Okay, that is the work done from O to A. Okay, then next up, I'm going from A to the point P. Okay, so I'm moving along the y-axis. So when I'm doing that, I'm going along this vertical line. So at any point on the vertical line, my x coordinate is fixed at 5, my y coordinate is variable, and my displacement is along the y-axis. Okay, so now for this second journey, yeah, from A to P, you can see that at a point 5, y, my force is becoming 20 I cap, okay, plus 10 y j cap. ऐसा बनना है ना? Because x is equal to 5 and y is equal to y. So, and my displacement ds is dy j cap. Okay, so my work done, okay, is becoming 10 y dy from y equal to 0 to y equal to 5. So the work done is becoming 5y square from y equal to 0 to y equal to 5. So it's becoming 125 joules. Okay, so now the work done in path 1, this total thing is the work done from O to A plus the work done from A to P. So it is 175 joules, positive of 175 joules. This is the work done for path 1. Okay, so I'm just minimizing this a little bit so you can go through it, check the calculation also, let me know if everything is fine. So this is O to A, and then this is A to P. So now this is the net work done. हाँ, because उसमें x का वैल्यू 0 था ना बेटा फर्स्ट पार्ट में. Oh, wait. This is a mistake. Wait. This first part is not correct. We are not at x0, no? We are at a general point x, 0. So the force is becoming how much? It's becoming 10 plus 2x I cap. Y is 0, x is not 0. No? And ds is dx I cap. So the work done, just make a correction here. This will be 10 plus 2x dx integrated from O to A. So it will become 10x plus x square. So it will be more than the value we had calculated from x equal to 0 to x equal to 5. So that will become how much? It will become 75, I think, isn't it? So this will become 50 plus 25. This value was wrong. The work done will be 75 joules from O to A. So just make a correction here. So this should be 75 plus 125. The total should come out to be. Yes, so thanks for pointing that out. So it should come out to be 200 joules. Yes, stage, that's correct now. Okay. So just make a note of this first, people. Okay, so the calculation is all right. You have double checked. So both these values are correct, 75 joules and 125 joules. Yes. Okay, very good. Now let's come to the second part. Now the second part is a little bit different compared to the questions we've done last time. So let me explain how we'll do it. Yeah, so for the second part now, we have to see that we are going along a straight line. So to get the displacement, we have to understand the geometry of the straight line. That is, what is its slope basically. And that's fairly easy to do because it's actually a straight line that is making 45 degrees with the x-axis or the y-axis and passing through the origin. So it's very easy to write the equation of the straight line. So it's not going to be difficult. Just we have to incorporate that part over here. So this next part of the question, we are going along this path, this 45-degree line. We are going along this let's say this point over here, which is our 5,5 from the origin. So you can see the equation of this line. The equation of the line is y is equal to x, because its slope, which is tan theta, is tan 45, and its y-intercept is 0. You see, this angle will be 45 because it's just a matter of observation. Right? So isosceles right angle triangle. Okay. So on this line, at any point, what will happen is our x and y coordinate will be such that y is equal to x. So at any point on the line OP, x coordinate is equal to y coordinate. Okay. So that means a small displacement along the x-axis is also equal to a small displacement along the y-axis. Okay. So a small displacement ds like this can be written like this, where again dx is equal to dy, because we are going along that line. Okay. So now the next thing, at that particular point, what about the force? So the force F, whose general equation is like this, 10 plus 2x I cap plus 2xy j cap, can also be written as 10 plus 2x I cap plus 2x square j cap, because y is equal to x at any point like this. Okay. And this ds can also be written as dx I cap plus dx j cap. Okay, because dy is equal to dx. So when we are calculating the work done in that path, okay, you can see that our integration f dot ds from O to P will become this 10 plus 2x dx plus 2x square dx, because we'll take the dot product of this and this. Okay, from the point O to the point P. So this will become integration of 10 plus 2x plus x square dx from plus 2x square dx. My mistake. The last term is 2x square dx. Okay, from the point O where x coordinate is 0 to the point P where the x coordinate is 5. So this will become further 10x plus x square plus 2 by 3 x cube from 0 to 5. So that will become how much? 50 plus 25 plus 2/3 of 125. How x square? Now, because x is equal to y. So in this force now we are substituting the fact that on the line OP at any point y is equal to x. This we are incorporating here. That's how we are getting this. So that's the thing. So that's what is particular about this path. So in this path now you can see the work done. Already you can see it's going to be different. The work done is going to be 50 plus 70, plus 25 plus 250 by 3. So that is 250 by 3, 83.33. Okay. So the work done is going to be 75 plus 83.33. So that is 160, sorry, 158.33 joules. That is the work done in the direct path OP, or basically the work done for path 2. So this is showing us that the force is non-conservative because the work done by two different paths between the same 2 points O and P are different. Okay, so I will just take you step by step through this a little bit. Okay, just hang on a second. So this is quite an advanced level problem. So don't worry that it's a bit complicated initially, but once you learn to analyze these types of problems, you will get used to it. How the angle is 45 now, which is the angle is 45, I'm coming to know from coordinate geometry. देखो कोऑर्डिनेट ज्योमेट्री में मैं कोई भी दो पॉइंट्स को जब ज्वाइन करता हूँ ना, यहाँ पे कोऑर्डिनेट्स 5,5 है, बट लाइन का स्लोप कितना होता है? m is equal to tan theta, which is y2 minus y1 upon x2 minus x1 ना, वो यहाँ पे कितना हो जा रहा है? 1 हो जा रहा है. That means theta is equal to 45 degrees. Or you can just drop this perpendicular and understand that this is a isosceles right angle triangle. So same way, suppose the coordinates of the point had been something else, like 2,3 or 4,5 or something, then my slope would have been different. Tan theta would not have been 1. This is just because it so happens that we have selected the point 5,5 in the question. So the slope of that line is equal to 1, or theta is equal to 45 degrees for that. Yeah, so Diti, in that case, we would have to write the equation differently. No? Then the question would become more complicated. Like, for example, suppose we had a situation where, let's just take an arbitrary example. So suppose my straight line was like this one. It's going from this point to this point. Let's say. Going from the point A, which let's say is 2, 1 to this point B, which is let's say whatever 5, 8. Okay, like this. So then any point on this line, the equation of the line first of all would have been like this: y is equal to mx plus c, which you would write like this, that y minus y1 is equal to m times x minus x1. In this we would put x1 y1 as the coordinates of A and x2 y2 as the coordinates of B, where m is y2 minus y1 upon x2 minus x1. So m will become 8 minus 1 upon 5 minus 2. So that is 7 by 3. So the equation of this line will become y minus 1 is equal to m, which is 7 by 3 times x minus x1, is this. So this will become y is equal to 7 by 3x minus 14 by 3 plus 1. So that will become minus 11 by 3. So this is the equation of the straight line. Okay. So now any point which has coordinates like this, x and y will be related like this. So at any point, the force which is acting, suppose that force is F like this, and the displacement from that point, if it is ds like this, so then the two things we'd have to do, but this would be unnecessarily complicated questions. So here the force, suppose that was 10 plus 2x I cap plus 2xy j cap. So we at that sort of point, we will substitute x as, or rather y as 7 by 3x minus 11 by 3. Okay, so this would become 10 plus 2x I cap plus 2x into this whole thing, 7x minus 11 by 3. This is your j cap component. And my displacement ds is equal to dx I cap plus dy j cap. तो इसमें क्या होता है, y is equal to 7 by 3x minus 11 by 3. So differentiate this. So dy would become 7 by 3 dx. So I would substitute this over here. Okay. And this ds would become dx I cap plus 7 by 3 dx j cap. Then I would take the dot product of this one and this one. So I would get f dot ds. And from that I would get the work done. No, this is too lengthy. Okay, the example I have given you is the type of example which you can expect at the JEE advanced level. I mean, this is also within your level to solve. There's no problem with that, but it's too lengthy for a JEE level question. This example is too lengthy for a JEE level question. Okay. So now that we have understood about conservative and non-conservative forces, okay, I will scroll up. All right. So before we move on, one thing we'll just finally note down here, that this shows us in this case that in this question, it implies that the force F is non-conservative, because the work done in path 1 is not equal to the work done in path 2. Between the same 2 points, the work done in path 1 and path 2 is not the same. So that means the work done is, yeah, I'll show that also. Okay. So, but before you come to the second sum was just an example, because Titi asked that what happens if the point is not the origin. So you can always solve a question like this by this manner, but it just becomes too lengthy to solve. That's the only thing. The method is the same, it just becomes too lengthy to solve. But yeah, coming back to this earlier question, you have to understand this point, that this actually shows us that the force is non-conservative, because the work done is path dependent. This is a path dependent quantity now. Okay, good. So next we move on to, so once we are clear about conservative and non-conservative forces like this, next we move on to the concept of potential energy. And we'll see that it has a relationship with conservative force. So what is potential energy? It is a form of mechanical energy, which can be, interconverted into kinetic energy and back from kinetic energy to potential energy. So it is a form of energy. Okay. In this particular chapter, you can say mechanical energy also, but it's actually more general. So it's a form of energy, okay, associated with the state or configuration of a system. Or configuration of a system. So let's understand this with an example. For example, the elastic potential energy. Okay. It is a form of energy stored in a spring. It is a form of elastic potential of energy stored in a spring. Okay. Or it can even be a rubber band. Okay. Or any elastic material. Okay. That depends on its state. That means its extension or compression, whichever be the case. Okay. And elastic potential energy can convert to kinetic energy. And vice versa during any process. Okay. So for example, we have a situation like this, that a block is moving on a surface, and at the end of it there is a spring attached to a wall. So the block will come and hit against the spring, and the spring will start to get compressed. Its state will change from natural length to L minus x, and the block, its speed will change to v prime. So v prime is less than v. As x increases, the speed decreases. Okay, so kinetic energy of the block is converting to potential energy of the spring. So this is an example of a process where kinetic and potential energy are interchanging. Elastic potential energy, beta dot nahi, potential energy. Elastic potential energy of the system. The definition is written here itself. Just note it down. Okay, no problem. Acha, this one na, I thought you were asking about this. This is potential energy. Okay, it's just, yeah, it's a short form for potential. You can just, okay. So anyway, so elastic potential energy kya hota hai? It is a form of energy that is associated with the state. Now obviously we haven't learned about this before, so we don't know the formula and all yet, but by general idea, what do we mean by elastic potential energy? Is the energy stored in the spring, which can, happen in such a way that kinetic energy is getting converted to potential energy, or in this case the block will eventually, it will compress against the spring, come to rest, and then the spring will push it back now. So when the spring starts pushing it back, and eventually the block again gets released by the spring, but moving in this direction. So again, now here, from here to here, what is happening? Potential energy is converting to kinetic energy. So this process can happen back and forth. Or like, if you have like a rubber band and you attach a block to it and release it from rest. Now the rubber band is at rest, rubber band is at natural length initially. So it's at some natural length L0. So after a while, what happens? It goes down, then eventually comes up. So again, here, what is happening in this system, it's a little bit more complicated, but in this system, kinetic energy of the block, okay, elastic potential energy of the rubber band, okay, and gravitational potential energy also. So don't worry about these terms just now. I'm just giving you a physical example. Gravitational potential energy of the block, because its height is changing. Okay, they will keep switching. Will keep interchanging or interconverting in this system. So this is just to give you an idea about what potential energy is. Okay, so far we haven't come to any relationship between potential energy and force and all those things. We'll come to that. Okay, so anyway, so as far as the concept of potential energy goes, we have understood that we generally denote potential energy okay with the symbol capital U, just like we denote kinetic energy generally with the symbol Ke. Okay, we can use the symbol Pe also for potential energy, but generally we use the symbol capital U. So this is elastic potential energy. Okay, of the rubber band. This is gravitational potential energy of the block. No, I'm not saying that it is gone to a compression. Okay, I'm still assuming that यहाँ पर भी it's on its way back to natural length. So it can be minus also. ऐसा नहीं है that it cannot be minus, but in my particular diagram, this is still in a stretch state. Okay, it can go to a compressed state also. That can also happen, but I'm just saying. Okay. So anyway, so potential energy we saw, it is defined for a system as the energy associated with its state, okay, or configuration. So from that we understand that delta U is equal to the work done to change the state of the system. So anytime we are changing the state of a system, we have to do some work to change it. And that is stored in the system as the change in potential energy. Change in potential energy equals to the work done to change the state of the system. So for example, if you want to understand that how much change in potential energy happens when we stretch a spring from 0 to x. So that change in potential energy will be equal to the work done to extend the spring. So for example, now if we have an ideal spring of natural length L, now to stretch the spring from x equal to 0 to x equal to some value, let's say d, an external agent will have to apply force and do some work. So that work done, okay, this will equal to the change in kinetic energy. Sorry, the change in potential energy. Of the spring. So to stretch it from this position to this position, this has to do some work. Okay. And that work done by the external force will become the change in potential energy of the spring. So this is the meaning of this statement, that delta U is equal to work done to change the state of the system. Yeah, we will understand all these terms. Elastic potential energy, gravitational potential energy, we'll understand in detail. So now let's do this calculation first. So when we are stretching this, what is happening now? If you look at the free body diagram of this, the external force we are applying is balancing this internal spring force. Okay. Its acceleration is tending to 0 because we are stretching it. So to stretch the spring slowly, okay, from x equal to 0 to d. Now, why we want to stretch it slowly? So that there is no change in kinetic energy involved. Okay. So there is no kinetic energy change. Only its state is changing. So the work done by the external agent will be equal to the change in potential energy, because there is no change in kinetic energy involved. So I want to do a calculation of change in potential energy. So I should do work in such a way that there is no kinetic energy change involved. There is only potential energy change involved. So its acceleration should be tending to 0. So to do this, F external has to balance Kx, because the acceleration is tending to 0. Tending to 0, beta. Very slowly moved now. It's tending to 0, not equal to 0. We can always have a motion in which A is 0. That's no problem, because velocity will be constant. But here we want the condition that is moving very, very slowly. So acceleration is tending to 0. So the force is tending to be equal to Kx. Understood? So when you stretch a spring very slowly now, you will not see the end point accelerating. You will see it moving very, very slowly from point to point. You are stretching it very slowly. So that situation. So the work done by the external agent in this case will become this. So that will become Kx dx from x equal to 0 to x equal to d. So you can see that the work done by the external agent is equal to half kd square. Okay, and because here change in kinetic energy is 0, so therefore the work done by the external agent is equal to the change in potential energy of the spring. So that is equal to half kd square. So the potential energy of the spring will increase by a factor of half kd square when it is stretched from 0 to d. So this is the conclusion that we're getting here. So it's tending to 0, na beta? Like see, first of all, in this case, we haven't attached any block. So the mass of the spring itself is negligible. Okay, but then also kinetic energy is half mv square. No? Now suppose your v is very small. It is like of the order of, let's say, 0.01 millimeter per second. Or even if it is 1 millimeter per second. Then your v square term is becoming of the order of 10 raised by minus 6. No? So your kinetic energy term will be negligible, no, compared to your potential energy term. So it's all about comparison actually. No? It's negligible compared to the potential energy. Yeah, we'll scroll up. Okay, now students, because of something urgent, I will be concluding our lecture a little bit early today. I have an urgent meeting to attend. So we will be concluding today's lecture here. We will continue from this point onwards in the next lecture. So continue with more examples from H.C. Verma. Do problems from H.C. Verma this week. Work energy chapter. You can do up to about question 33 or so. Yes, I will send the notes of both last lecture and today's lecture. I think one lecture notes are pending. I'll send the notes and the videos. Okay. So that's it for today's session, people. Wish you all the best.